Okay, 2.52, rather interesting mathematical sort of problem. So we are given this hyperbolic secant potential. In part A, we're asked to graph this potential. So that's pretty trivial. We can literally just throw this into Desmos, or if you know what hyperbolic secant actually looks like, you would also be able to infer that this has the shape of a bell curve. So if we were to graph this out, and you know what, excuse me, I'm going to use straight lines to make this a little bit nicer. If we were to graph this out, the negative of hyperbolic secant squared looks like a bell curve, something like this. And that's it for part A. So we move straight on to part B, which says that we want to check that this potential has the following ground state. And I actually didn't get the screen capture in for the actual wave function, so give me 1 second to reset this. There we go. Okay, so this is part B, which is to say that we want to check that this hyperbolic secant potential has the following ground state: psi naught of x is equal to a hyperbolic secant of ax. Now, I don't really like the way this question is worded. I think this is a pretty poorly worded question, because at this point we don't actually have a way to verify if this given wave function is actual ground state or not. We have no way of knowing if there are lower states that have lower energies. The only thing we can really verify is whether or not this wave function itself is an actual valid wave function, and we can find the associated energy by using the Schrodinger equation, but we don't really have a way of verifying whether or not this is an actual ground state. So I think the way this problem is worded is a little bit problematic as a result of that. In reality, what it should be saying is that check that this wave function does in fact is in fact a valid solution for the given potential, and assume that it is the ground state and find its corresponding energy. So we don't know if it is the ground state. We have no way of verifying that, but all we're going to do in part B is we're going to check that this is actually a valid solution to this given potential, and we're going to assume that it's the ground state, and we want to find its associated energy. So to do that, we're pulling out the tried and true Schrodinger's equation, negative h bar squared over 2m times d2 psi by dx squared plus the potential multiplied by psi is equal to e psi. So if we plug this in, we have our potential. V is equal to negative h bar squared a squared over m's hyperbolic secant squared of ax. And then we have our wave function. What we should get is negative h bar squared over 2m times the second derivative of a hyperbolic secant squared, or sorry, but yeah, a hyperbolic secant, not squared, just a hyperbolic secant of ax, and then subtracted by h bar squared a squared over m times the potential, which is going to be hyperbolic secant squared of ax, and then multiplied by the wave function, which is going to give us another a hyperbolic secant of ax. And we want to show that this expression evaluates to, some constant multiplied by our wave function. So let's do that now. Okay, so to actually do this, we need to know what the derivatives of hyperbolic trig functions actually are. And in this case, we're going to need two. So I'm going to write them out now. If y is equal to hyperbolic secant of x, then the corresponding derivative that comes with that is going to be equal to negative hyperbolic secant of x multiplied by hyperbolic tangent of x. Alternatively, if y is equal to hyperbolic tangent of x, then the derivative is going to equal hyperbolic secant squared of x. So these are the only two we need. And if we were to solve this now, then we would get negative h bar squared over 2m. We pull the a out, and then we have the second derivative. So we derive hyperbolic secant once, and we get negative at the front, d by dx of hyperbolic secant x times hyperbolic tangent. My apologies, there's supposed to be an ax. Ax times hyperbolic tangent ax. And then we close this off. And then just like any other derivative of trig functions, we have to utilize product rule. And the derivative of ax with respect to x is going to give us a. So we're going to pull out a factor of a at the front here. And then we're subtracting by a times h bar squared a squared over m times hyperbolic secant squared ax. Multiplied by another term of hyperbolic secant ax. So this gives us hyperbolic secant cubed of ax. And this is supposed to equal some constant a times e times hyperbolic secant of ax. So immediately what I see is I can cancel out all the a terms, which is nice. And what I'm left with, the two negatives make a positive, so we have h bar squared over 2m. And then we're going to use product rule once again here. So this is going to be, let's see, d by dx of hyperbolic secant of ax. And then multiplied by hyperbolic tangent of ax. And then we're added with hyperbolic secant of ax times d by dx of hyperbolic tangent of ax. And then we're subtracting by h bar squared a squared over m times hyperbolic secant cubed ax. And this is equal to e times hyperbolic secant ax. Now let's do the actual derivatives. So for this is going to give us, let's see, h bar squared over 2m, and then negative hyperbolic secant times ax multiplied by hyperbolic tangent squared times ax. Pull out the factor of a at the front. And you know what? I forgot to pull that in, so there's supposed to be an a there. There we go. We pull out this extra factor of a via product rule. Then we have the derivative of hyperbolic tangent, which is going to give us hyperbolic secant squared. So there's going to be hyperbolic secant cubed of ax, once again multiplied by a factor of a due to product rule. And then we're subtracting h bar squared a squared over m times hyperbolic secant cubed ax. And this is equal to e hyperbolic secant ax. Next, immediately I see that there's a common hyperbolic secant term everywhere, so we can pull that out. What we're left with is h bar squared a over 2m minus, what's this going to be? Negative hyperbolic tangent squared ax. And I'm going to pull the a out of the interval here. So this is going to be h bar squared a squared over 2m. And then we're adding hyperbolic secant squared times ax. And let's see. Yeah, that's correct. And then we're subtracting by h bar squared a squared over m times hyperbolic secant squared ax, and this is equal to e. And then I can multiply this into the inner term. So if I multiply by a factor of 1/2, let's see. Yeah, so this can be rewritten as, this lower term here can be rewritten, and I can put it into sort of my inner sum in this parentheses right here. If I rewrite this as h bar squared a squared over 2m, and then multiplied by 2 hyperbolic secant squared ax. So if I do that, then I can rewrite this whole thing as h bar squared a squared over 2m times negative hyperbolic tangent squared ax plus hyperbolic secant squared ax minus 2 hyperbolic secant squared ax. And this is equal to e. If I rewrite this and pull out the negative, then we get negative h bar squared a squared over 2m is going to equal hyperbolic tangent squared ax plus hyperbolic secant squared ax. This is equal to e, and we're basically done because this is a trigonometric property. This expression equals 1. If you want to verify this, you can redefine the hyperbolic tangent and hyperbolic secant in terms of complex exponentials, add together their squares, and you can see for yourself that they do in fact equal 1. I'm not going to do that because that's a very tedious mathematical process. So I'm just going to get that the ground state wave function is therefore equal to negative h bar squared a squared over 2m. Next, they want us to normalize this. So to normalize this, what I'm going to do is I'm going to take, the integral of the magnitude squared of this wave function, set it equal to 1. So if I do that, then 1 is equal to the integral from negative infinity to infinity of magnitude psi naught squared dx. There's no imaginary terms here, so this is effectively the same thing as just taking the integral of the term squared. So this is going to give us a squared times the integral from negative infinity to infinity of hyperbolic secant squared ax dx. And at this point, considering what the integral that we did earlier, you should already know what this answer is, because we know that there's this property, which is that y hyperbolic tangent of x, given that the derivative is hyperbolic secant squared of ax. So if we add the a, then given that y is equal to hyperbolic tangent of ax, then the derivative y prime is going to equal hyperbolic tangent. It's going to equal hyperbolic secant squared of ax multiplied by a. So if we do that, then this is going to give us that this corresponding integral is equal to a squared, and then multiplied by 1 over a times hyperbolic tangent of ax evaluated from negative infinity to positive infinity. Hyperbolic tangent, if you graph it out, goes to 1 and negative 1 at infinity and negative infinity respectively. So this is going to give us a squared 1 over a multiplied by 1 minus negative 1, so plus 1. And this is just equal to a squared 2 over a. So that means a squared is equal to a over 2, which means that a is equal to root a over 2. So the actual correct wave function is psi naught of x is equal to root a over 2 multiplied by hyperbolic secant of ax. And that is part B finished. Okay, part B has multiple parts, so I'm going to take this one at a time. We want to start by showing that this super complicated function, psi sub k, where k is equal to root 2me over h bar as usual, solves Schrodinger equation for any positive energy E. So what we're trying to show, therefore, for this first part, is that this psi k can be plugged into Schrodinger's equation and gives us a valid solution for any arbitrary value of E. So immediately, I'm tempted to just take the second derivative of this term, because I know that the Schrodinger equation looks like negative h bar squared over 2m times the second derivative of psi with respect to x squared minus h bar squared a squared over m times hyperbolic secant squared ax times psi of x is equal to e times psi. And I'm going to replace all the psi's with psi sub k's. So immediately I want to take the second derivative. Another thing I can recognize is that, a is a constant. It's going to come out of the second derivative as a constant at the front. There's going to be a constant a here, and there's going to be a constant a here. I can just straight up ignore the a and just pretend that it doesn't exist, because it's going to cancel out at the end anyway, just to make my life a little bit neater. So now that we have this, let's rewrite psi and take its derivatives. So let's do this in red, actually. So I know that psi of k is equal, and I'm gonna write this out fully. So I'm gonna do I'm gonna write this out as what is it? Yeah, ik over ik plus a times e to the ikx, and then subtracted by a over ik plus a times hyperbolic tangent ax times e to the ikx. And this is going to make my calculations a tiny bit easier, because I've split this into two things that are more easily manageable than one big thing. The first derivative of psi k is then going to equal, I'm going to pull out an ik term, so the two ik's make a negative k squared over ik plus a e to the ikx, and then we're subtracting by a over ik plus a, and then we're doing product rule now. So the derivative of hyperbolic tangent, if we look up here, is hyperbolic secant squared. So hyperbolic secant squared ax times e to the ikx. We're going to pull out a factor of a because of product rule. And then we're adding ik hyperbolic tangent ax e to the ikx. And in fact, I can make this even simpler on myself by pulling out the e to the ikx factor, leaving me with hyperbolic secant squared ax times a at the front plus ik hyperbolic tangent ax. Okay, so rewriting this, the first derivative is therefore equal to negative k squared over ik plus a times e to the ikx, subtracted by a over ik plus a times a hyperbolic secant squared ax plus ik hyperbolic tangent ax times e to the ikx. And in fact, I can simplify this even further, but I think for now I'm going to leave it alone. So now the second derivative is going to give us negative ik times k squared ik plus a times e to the ikx, subtracted by a over ik plus a. And now we're deriving this, so this is going to give us 2a hyperbolic secant ax, and the derivative of hyperbolic secant, which is going to be a negative at the front times a square of hyperbolic secant and then hyperbolic tangent ax, and then multiply by a factor of a again because we're pulling that out. And then we're adding ik times hyperbolic secant squared ax, and then we're adding a factor of a at the front, and then multiplied by e to the ikx, and then we're subtracting a over ik plus a times another factor of ik, and then multiplied by everything here. So we're just doing product rule here. So this is definitely a very disgusting looking function. So let's see if we can simplify a little bit. Yes, I can. I already see some simplifications we can do. So I can rewrite this. d2 psi k by dx is going to equal the same at the front, so negative ik times k squared over ik plus a times e to the ikx. And then we are going to subtract by a over ik plus a times e to the ikx, and then negative, whoops, this is a bit messy, negative 2a squared hyperbolic secant squared ax hyperbolic tangent ax plus ika hyperbolic secant squared ax, and then I'm going to combine with the lower term, move the ik in, so minus ika hyperbolic secant squared ax, and then this is going to give us, let's see, actually this is plus because the minus is already taken out of the factor. So plus ika hyperbolic secant squared ax, and then this is going to be minus, because the ik multiplies with the ik to make a minus k squared hyperbolic tangent of ax. Okay, these two are going to combine. We're going to get d2 psi k by dx squared. I forgot the square down here as well. And this is equal to negative ik times k squared over ik plus a times e to the ikx, subtracted by a over ik plus a times e to the ikx, and then negative 2a squared hyperbolic secant squared ax hyperbolic tangent ax plus 2ika hyperbolic secant squared ax minus k squared hyperbolic tangent ax. Okay, now we plug this back in to the top here. So what's this going to give us? Negative. So the two negatives make a positive. So I'm going to actually rewrite this as h bar squared k squared over 2m, and then put the ik inside. So ik over ik plus a, just to conform with sort of what we've been working with so far. E to the ikx, two negatives make a positive, and then we're adding, because two negatives make a positive once again, plus h bar squared over 2m times a over ik plus a times e to the ikx, and then multiplied by this expression, which I'm just going to copy paste. And this is getting subtracted by, and let's put this in black, h bar squared a squared over m hyperbolic secant squared ax multiplied by psi k, which I'm going to copy paste from here. In red, once again. And this is going to equal e times psi k. So let's see how we can simplify this. Well, immediately I see that I can pull out the e to the ikx for every term. So that's going to leave me with h bar squared k squared over 2m times ik over ik plus a plus h bar squared over 2m times a over ik plus a multiplied by negative 2a squared hyperbolic secant squared times ax hyperbolic tangent ax plus 2ik a hyperbolic secant squared ax minus k squared hyperbolic tangent of ax. I just realized I forgot to close this parentheses. And then subtracted by h bar squared a squared over m hyperbolic secant squared ax, and then multiplied by ik over ik plus a minus a over ik plus a times hyperbolic tangent ax. And this ultimately equals e, and then remember that the a and the psi k got canceled, and the e to the ikx and the psi k got canceled, so we're left with the exact same expression over here that gets pulled down. So somehow we want to get the upper terms into something that looks like this, so that way we can do a little bit of maneuvering. So let's see, give me 1 second to look through this problem to see what the next step should be. Okay, so I'm going to start by writing this out fully. So if I do that, then I'm going to get, let's see, h bar squared k squared over 2m. And you know what? This is such a long expression that I actually have to divide up my partitions. Ik over ik plus a. Then the first term of the set is going to be plus h bar squared a squared. And you know what? The positive and the negative turns into a negative. So minus h bar squared. I'm going to move the a squared to the front, get rid of the 2's, I'm left with an m term. And then multiplied by a over ik plus a, multiplied by secant hyperbolic squared ax times tangent hyperbolic ax. Is that correct? Negative, the 2's cancel, h bar squared a squared over m. Yeah. And then I'm going to add, let's see, h bar squared. I'm going to combine the a here with the a here. I'm going to move it into the h bar squared term. So h bar squared a squared. The 2's cancel. I'm left with h bar squared a squared over m. Ik over ik plus a. And then multiplied by hyperbolic secant squared ax, I believe. Is that correct? H bar squared over m. A squared. Ik, yeah. And then finally, subtracting by h bar squared k squared over 2m times a over ik plus a times hyperbolic tangent of ax, I believe. H bar squared k squared over 2m, yeah. And then expanding out this second term, this is going to be minus h bar squared a squared over m ik over ik plus a times hyperbolic secant squared ax. And then we're adding h bar squared a squared over m times a over ik plus a hyperbolic secant squared ax hyperbolic tangent ax. And this is supposed to equal e times ik over ik plus a minus a over ik plus a hyperbolic tangent ax, where this term is psi k effectively. So if we do that immediately, thankfully, I see that there's some stuff that we can cancel, because we have an h bar squared a squared over m ik over ik plus a hyperbolic secant square term that we cancel out immediately. Over here, similarly, there's another term here that we can cancel out, the h bar a squared over m times a over ik plus a hyperbolic secant squared times tangent hyperbolic. So what we're left with are two terms, which is significantly easier to work with. We have h bar squared k squared over 2m times ik over ik plus a minus h bar squared k squared over 2m over a times ik plus a times hyperbolic tangent ax, which then immediately simplifies down to h bar squared k squared over 2m times ik over ik plus a. And this is a bit of a typo here. It's not ik, it's ik plus a. My apologies. Subtracted by a over ik plus a times hyperbolic tangent ax. And if you go back up here, we realize that now we have the same psi k term, so therefore the energy is equal to h bar squared k squared over 2m. Now, at the start of the problem, we were told that k is the usual value of square root 2me over h bar. So if we plug that in, then we get e is equal to h bar squared over 2m times 2me over h bar squared, which implies that e is just equal to e, which means that this solution does in fact allow for wave functions of any arbitrary energy level e, because no matter what we plug in for e, we always get e equals e, which means that that energy is always going to be allowed. So therefore, every single possible energy from any wave function is a valid solution to this corresponding potential. Okay, this last part says that since hyperbolic tangent goes to -1 as z goes to -infinity, psi of k approaches the expression a e to the ikx at very large negative x. Now, if you remember, when we started treating free particles, a e to the ikx represents a free particle coming in from the left. Because remember, in general, for a free particle, the wave function is defined as a e to the ikx plus b e to the negative ikx, where this term is motion from the left coming to the right, and this term represents motion to the right coming from the left. So, evidently, at very large negative x, so when we're very far away to the left of this curvature, because remember, our well is a inverted Bell function, right? So this just looks like a standard potential well, but evidently, from the left, the particle only looks like a incoming wave from the left and does not have the wave function corresponding to the particle moving to the right, moving from the right to the left. It only has the wave function for moving from the left to the right. So this is very strange because typically when you have a potential well, something like this, you expect that you have an incoming particle, that comes in, and then it meets this boundary at some point, and it has a probability of either transmitting through it or a probability of being reflected back. So the fact that the wave function at infinitely far away takes on the form of just ae to the ikx without the be to the negative ikx part implies that there is never ever actually a reflection. There's no probability of there ever being reflection in this system as a result of a hyperbolic secant potential. And that's very weird. That's not what we would expect, because everything we've treated up to this point in free particle cases is that whenever you have an infinite, or not even infinite, whenever you have a potential well or a potential barrier, and you have an incoming free particle, you always expect it to either transmit through or reflect back. Now, the probability, and therefore the magnitude, of the wave functions corresponding to reflection and transmission may be different. They might be bigger or smaller depending on what type of potential you have, what type of energy you have for your particle. But overall, there should always be a be to the be to the negative ikx term to represent reflected motion. The fact that there isn't one here is very unusual. So we are asked to find psi of k at large positive x. So we can recognize that at tangent hyperbolic of x goes to positive 1 as x goes to positive infinity, in which case our wave function psi k is going to approach a times ik minus a times 1 over ik plus a times e to the ikx. So exactly the same. This is just going to be some constant. Ik minus a over ik plus a is some constant. A is some constant. The only x dependency is in e to the ikx. So what this means is that for our infinite, or not for, I don't know why I keep saying infinite well, but for our finite potential well, defined by a hyperbolic secant function, when we're really far away here, the wave function is approximately equal to, some constant b times e to the ikx, which represents motion from left to right. And really far to the left, our wave function is approximated as ae to the ikx, which also represents motion from the left to the right. So, because of the fact that this be to the negative ikx term doesn't appear, this implies that the particle is never going to be reflected back. It always transmits through, which is very unusual once again. And if you're confused about what this implication, remember that psi of x determines probability. So if we take the magnitude squared of the wave function, this gives us a probability of the wave being, or of the particle being in some location. So if there is a non-zero probability of the particle reflecting backwards, you need to have the wave function correspond, or at least include that type of motion in it, so that when you take the magnitude squared, that probability actually shows up. So here, by not having a be to the negative ikx, this sort of implies that our particle is never going to reflect, and therefore we have a reflectionless potential. Now, the actual physical reasoning behind this is a little bit beyond the scope of chapter 2. You'll be able to sort of analyze this more closely when we start going into the later chapters, where we start using more advanced techniques. But at this point, sort of, we're limited to just appreciating this one solitary example of a reflectionless potential. Evidently, there's something very weird or something very special about the way hyperbolic secant, or it just inverse hyperbolic trig functions in general work, which seem to, when plugged into the Schrodinger equation, give rise to very unusual behaviors like this. Finally, we are asked to find r and t, and that's pretty obvious at this point. R is obviously just going to equal 0, and t is obviously just going to equal 1. And with that, we are done with this problem.